But so like this looks pretty simple from the outside, other than this one little sort of telltale hole up there. And so if we take a cross-section of this part, it's actually far more complex and basically hollow. See, and it's a real-world example. He just gave me this part just now, and so that is a lot of the parts I would love to show you can't, because I would get in trouble if I showed you how they make a jet engine or something like that. But this is definitely a fantastic example, and of course it's got the, if you notice, let me flip it around. All of these surfaces are basically slanted so that the metal powder or whatever the support material it is, this is, you said, carbon fiber and stainless steel. So this has got all the, for the support material to pour out through these holes. It's very important to remember to put a hole running through your whole part so the powder can come out. If you don't do that, it basically becomes a solid part full of like a shaky powder or just a not as dense powder, which is possibly not optimal / costs more money. And so the more powder you can save by removing material, the better. This is actually a really cool part and designed really well. And so if we just like pan a cross-section through it, like that's a pretty easy CAD model. And then designing this up front in CAD is very little time comparatively to like printing it out and testing it and seeing it doesn't work or going back and forth between different metals or trying to figure out specifically like the very fine tuned parameters of each machine. Like maybe this didn't work at in solid, but like if he'd spent 4 years fine tuning that machine, it might have worked in solid, or it might have worked as a solid part. Versus if you just optimize it and change the geometry, it could work right away, immediately, and in fact, in this case, actually be stronger. So that's a super cool application and a really useful real world one. That's a good one. I actually don't know a whole lot of. We don't do a lot of inspection in our office. I do know a lot of it is done, our inspection's done through, with like capture scanners and going through and basically just scanning the object and then printing it off. I'm assuming just from my sort of fundamental knowledge of the inspection process, it would be difficult to inspect, say, this part without like an X-ray scanner to be able to see all the internal parts. So depending on the complexity of your part, it probably varies a little bit. So I know for like, if you were just using our capture, for instance, and say our Geomagic Design, I think it's Geomagic Control software, which might be our inspection software, then you can do delta maps. And so a lot of times I'll print out a part and then map it back to its original STL to see what the differences are. And so hopefully it's within 50 microns or less of the part. But of course you can only scan the outside of an object. And so anything like this part, for instance, I could tell you it was the right shape, but I couldn't tell you if all of the internals were correct without having possibly taken an X-ray scan of it or just slicing it in half and looking at it. But this is a good question. I should look up more of that. I don't know a lot for design for inspection. Yeah, so I actually sort of like, there are softwares, I don't have any on this laptop, that will sort of basically optimize for thermal stresses. Not even so much thermal stresses, but like you can basically be like, where's it gonna get? It'll show you with a nice like heat map of where the thermal stresses are, and then a lot of times just in CAD, because I have basically unlimited resources with a 3D printer, or like unlimited resources and complexity, like maybe if I'm making a drill bit, do I even have a drill bit? I might have one, actually. No. But let's say if I'm like, what would be an example of a part you would be optimizing for heat? A lot of times I would probably just do that in the geometry itself, possibly by just, and solid thinking might, let's click. I have not clicked on the 2016 version very much since I've got it for about a day. But I do know there's a lot of like softwares that will at least give you a heat map so that you could at least design your CAD files around that specific application rather than, let's see, structure, stamping, temperatures. So without having actually ever pressed any buttons in here, I'm flying blind, but you can totally do at least stuff with, there is a temperature button, so I'm assuming it'll do at least some basic rudimentary maps. So I haven't done it to any parts that actually got in actual applications, because that was normally, we don't, Boeing won't let me design their stuff. And so, but a lot of times we'll design basically equivalent of like a generic die or like a generic thing that will then spit out, like, be like, this is how you would do it. I don't know what you're making, but like, would be my suggestion on how to go about it. And so there's also like running fluids through parts. I'm a big fan of like running internal plumbing through parts to cool parts. So like a lot of drill bits we'll have, instead of like just flushing the whole drill bit with a coolant, we'll actually run channels through the insides of the drill bits. And so like say with your fuel injector, you could run, I mean, we can be like a rocket engine and we can run the cold fuel through the nozzle of and then back through it, and versus like, and at the scale of, I'm assuming a fuel injector is pretty small for a car, right? Automotive? Aerospace, sorry, got the industry confused. But like a decently sized fuel injector, like probably still too small to like weld all of those little tiny plumbing fixtures onto the inside of an object to try and actually get it to cool. But in here, in CAD, it's pretty easy just to like, what is it? If I make a cylinder and then curve spiral, let me turn my center snap on. Oops, wrong axis. But I mean, like, I could very easily just pipe that curve. And maybe I even vary the diameter of the pipe. So like maybe at the very beginning, there's no thermal stresses at the, what's going on? Wrong button on the keyboard. At the very beginning of this pipe, maybe there's no thermal stresses going on, so I don't really need a lot of surface to air, or surface to part. I'm trying to think of what it would term. I'm drawing a blank. But maybe at the bottom of this part, I need a lot more surface area. And so now I've got a tapering pipe that runs through, and I'm just going to scale it. But like maybe it runs through the inside of my pipe, my object. Let's just make it cool. Another cylinder. Sorry, trying to catch the center there. So then I'm going to actually scale this in slightly more. Oh, they don't intersect. All right. Cool. So if I take a cross section of this part now with like a pretty easy CAD model there when I wasn't even really paying attention to the exact details in here, but like now I've got, and there's some intersecting pipes going on, but that'd be a pretty easy way to like very quickly CAD model. And if you printed this in metal and then pumped fluid through it, keep it cool or hot or whatever temperature you would like to keep it at. And so, and of course, you could then like determine even the shape of this pipe. Like maybe a spiral pipe is not the best. Maybe you want it instead of sweeping a circle along that pipe, you could sweep a star to increase the surface area, or you could sweep another type of shape, like even maybe some sort of squiggly, like sort of organic, kind of like like an anemone type shape along that line. That maybe like you would never think about sweeping one of those shapes along it because you could never machine it. But now I can. And so like, not machine, but like now I can make it in real life. So now it's sort of getting into the biomimicry area of things, like what is the best possible way of like, say, throwing heat off an object or maybe filtering something through, like if for instance, you're trying to think of an example of heat, like on, trying to think of like not a butterfly wing, but there's some animal wings, like on say a mammal's wing, like a bat wing, there's probably the loss of heat, I'm assuming, is probably done through the skin flaps on there. And I bet if you were to study the vascular structure on one of those things, that might give you a decent way of like getting rid of heat through a very thin structure. Or there's a lot of like sort of biomimicry inspiration to be found just looking around at nature and how they do it, because it's no longer that hard to make these things. I've seen some structures. There was a bracket on a plane that was done basically, the structure on it looked like the bottom of a lily pad. And that was they were just going for a nice rigid structure that was really light, and so they've got a bunch of like 1 millimeter thick sheets going along the bottom. And it's not just a box, it's like a standard box or even just a standard grid. It's this beautiful, like a lily pad structure, because it's being supported at one point in the back versus like along a whole wall. So there are some limitations to things. It depends on the specific process. And so if this was a DMP part, and if I didn't use sloppy CAD modeling and cause those intersections, a lot of times the powder inside a DMP part is fine enough that it should just pour out of a lot of pores, like a lot of basically capillaries. I think the thinnest I've ever gotten anything to pour out is 0.5 millimeter. But I don't have a lot of experience. But like if I can have basically a tube that's anything bigger than 0.5 millimeter, the support material should just pour out of it. I might have to sit and like rotate that part a bunch of times in a row to make sure all the powder pours all the way out. Or maybe I stick an airline on one side and put some pressure behind it. But that's definitely a consideration. That's one of the reasons why I like SLA a lot, because it's a liquid, basically liquid, and so it just drains out, which is super nice. But with DMP, particularly some of the compressed metal powders, so if you compress it each layer, or the semi-centered stuff, it gets much more complicated into that design process, because maybe you can print it, but of course you can't get the support material out, so then it's useless. But we have, and I of course don't have one, but we've got a lot of like water jackets. There we go. We've definitely got, I wish I had brought it with me, should have done that. We have there's definitely some parts that have water jackets running around the outside. And so like the whole part, and it's just like an example fuel injector, but the wall thickness on this part is 0.5 millimeter on the actual structure, and then there's maybe 1 millimeter of water going around the outside of the part through multiple different channels, and then another 0.5 millimeter wall thickness going on the outside of that, and then of course some plumbing going in. And they just flush those as fast as you can to keep the heat off. And so I wish I had that to show you guys. That'd be really cool. But just definitely those examples online. If you type in like 3D printed water jacket, there's definitely an enormous amount of examples. To continue on your question though, there's definitely, and there's also, I've noticed a lot of times we were printing basically a part for a big filtration system, and they had handed me a block of steel, and they decided for whatever reason that their company would like to now start printing these objects because they were too hard to machine before. And so, but then it was too expensive to print them at this point, so my job was to basically hollow out this part while maintaining that strength. And so once it was hollowed out, and I sent it to our parts facility, and that's where we've got all of our big metal printers. One of the cleaning people was like, hey, could you put a second hole in because I had one hole in the bottom for powder removal. Like for instance on this part, if you had just one hole in the top, it'd be really difficult to get that powder out. But since I put 2 holes in it, or not since his designer put 2 holes in it, you can now put pressure on one side and have it go out through the other, which makes it so much easier to clean. And so that's definitely some techniques of also you've got to be able to sometimes fit something in there to help it out. Like maybe you need to basically run a quick like a dental pick through the inside of it. Just a dental pick's an example, but just something tiny run through to kind of break up that powder a little bit more before it pours out. But I know a fair amount of our specific machines, but I know a lot of the metal powders are so fine that they almost act as a fluid if they haven't been centered yet. So when they're still in the non-centered stage, they're, I would say, closer to a fluid at some level.